Hey everybody, Professor Monty here. Today we're jumping into chapter 10. We're jumping right into section 10.2, Inferences for two population means, sigmas assumed equal, and we'll be using StatCrunch to do our calculations. So inferences for two population means, we're looking at two separate populations to determine something about their means. So the inferences, we will be doing hypothesis testing to see if the means of the two populations are the same or different. We'll also be doing hypothesis testing on the same thing. So again, the sigmas are assumed equal. In other words, the population standard deviation of each of the two populations we're assuming to be equal in this case. In the next section, 10.3, we'll assume the sigmas are not equal, and we'll see how we have to address things in that case. Okay. So let's jump into the assumptions first off for doing either confidence interval or a hypothesis test. So the assumptions are very similar to what we've seen before. First of all, it has to be a simple random sample. Second of all, since we're talking about two different populations, one of the things we have to make sure is that we have independent samples. And remember what that means is the selection of one of the samples cannot be influenced by the selection of the other sample. And then number three that we've seen this one before, we either have to have normal populations or large samples. And remember, by large samples, we usually talk about n has to be greater than or equal to 30. And then in this section, we're assuming sigma sub 1 is equal to sigma sub 2. So the two populations have the same standard deviation. Okay, so those are our assumptions. Let's go ahead and talk about this. Now, let me give you a quick note right here. You may remember what we're going to be doing. We don't know sigma in this case, so these aren't going to be z-tests, they're going to be t-tests. We're assuming sigmas are equal. We just don't know what they are. So we're going to have to do a t-test in t-intervals. Well, since we're doing t's, we usually talk about degrees of freedom. And remember, with a single population, the degrees of freedom are the sample size n minus 1. Well, since we have two sample size, the degrees of freedom n1 plus n2, so the total of the two samples, and then minus 2, since we subtract 1 from each of the two samples. Okay, that's my degrees of freedom. We may or may not need that as we go. We're not going to use it in calculations, but we will see it being calculated. Okay, now here's the big thing we haven't seen before. For the null hypothesis, what we're going to be doing with the null hypothesis is we are going to be checking to see if the means are equal, the population means. So mu1 is equal to mu2. And so those little subscripts of 1 and 2, that mu sub 1 on the left just means the population mean from the first population, and then the population mean from the second population. That's the mu sub 2. So the subscripts just tell us which population it's coming from. Now, from that, sometimes the way you'll see it, and actually how StatCrunch does it, is if we're assuming the two means are equal, that means there's no difference in the sample, in the population means. So another way they can write that is that mu1 minus mu2. Well, if they're equal, that has to equal 0. And that's how StatCrunch writes it. So I want to be clear about that. From there, we may have a less than, we may have a greater than, we may have a not equal to 0. So it just depends on what we're testing. Okay, the other thing that comes in here, since we're assuming mu1 equals mu2, sigma 1 equals sigma 2, since we're assuming the populations have the same standard deviation, what we're going to do is we're going to do what they call pool the data. We pool the data. So remember, we usually, since we don't know the population standard deviation, what we usually do is we use the sample standard deviation to approximate the population standard deviation. And that's why we have to do the t-test and the t-interval in the first place. But since we're assuming these are equal to each other, both populations have the same standard deviation, what we're going to do is we're going to put both of the samples together so that we get a sample standard deviation based on all of the data, not just one of the two samples. That's what we mean by pooling the data. That will lead us to more data to hopefully get a better approximation of what the population standard deviation is. So if we can make the assumption that the two population standard deviations are equal, we always pool the data in that regard. And you'll see that we type that in to StatCrunch to pool the data. Okay, and then just recall lastly, doesn't look much like a C, does it? Recall, since we don't know the population standard deviations, we assume they're equal, we just don't know their value. We use t-intervals and t-tests. And by saying that, not z. So we're not using the z-interval or z-test, we use t-interval or t-test. And from there, let's just jump in. We're gonna do a couple problems and I'll show you how this works. So let's jump into our problem set. And I've just picked up a couple problems that we're gonna do, starting with problem 8. So let's see what that one's all about. All right, so here's our problem. It says preliminary data analyses indicate that the assumptions for using pooled T procedures are satisfied. So remember, we're assuming sigma 1 equals sigma 2. Independent random samples, well, that's good, of released prisoners in the fraud and firearms offense categories yielded the given information on time served in months. At the 1% significance level, do the data provide sufficient evidence to conclude that the mean time served for fraud is less than that for firearms offenses? Okay, so when we look at this, a couple things we want to make sure to note. When we open this up, they have fraud, then firearms. And then the question says, 1, at the 1% significance level, so I know alpha is 0.01, do the data provide sufficient evidence that the mean time served for fraud, that was the first one, is less than that for firearms? So my null hypothesis is that mu sub 1, the average time for fraud, is equal to that of firearms. But the alternative hypothesis is going to be mu 1 is less than mu 2. And so that's what we're going to look at here. And again, what StatCrunch is going to do, they're going to say mu 1 minus mu 2 is equal to 0. Or mu 1 minus mu 2 is less than 0. I like to set it up originally that first way. And in fact, when we look at the problems in my stat lab, we see that they do set it up the first way. They will set it up the second way though in StatCrunch. So we have to understand both of those. So when I look, let's figure out which one of these is the correct answer. Well, on A, the null hypothesis is right, but the alternative is backwards. So it must be C. So we'll check that. All right, so we got that right. So let's keep going from there. Compute the test statistic T. So now we're doing the hypothesis test. Remember, we know that the significance level alpha was 0.01. Well, I'm going to find the T value and I'm going to find the Z value. So let's find T and Z. These are both going to be straight from the test. So they give us the summary statistics, but instead of writing those down, I'm just going to use the data and have StatCrunch do it for us. So this is going to be a little bit different than what we've done. So let's get that data up and I'll show you what we're going to do with it. Okay, so there's our data, and they're showing us for fraud and firearms. Open it up in StatCrunch. And what I'm going to do is I'm going to do a t-test, but we haven't done one of these before. It's a 2-sample t-test because I have 2 samples, one from each population. So when this comes up, it's going to look very similar to what we've done before. And again, if you get a problem like this, just sign into StatCrunch and let's see, sign in. So a lot of times you can just go straight in and just go back and it'll reload for you. But I have to go through a couple steps, not a big deal. So it loads it up in StatCrunch. I don't have any of my data there. Apparently I'm going to have to go back and open it up myself. Nope, not there. So it didn't pull up my data, so let's go back to the problem. Here it is. We'll try to open it up in StatCrunch again. And sometimes you run into that problem, sometimes you don't. It's no big deal. But a lot of times you just need to try to open it up again, and usually on the second time it'll open right up. But sometimes we do have that issue. Okay, so now we're opening it up, so you see it's loading the data. So it's got 2 columns of data here before. And so what I'm going to do is I go into stat, T-stat, because I'm running a t-test. But this time it's 2 samples. And then with the data, because I have all the data, not just the summary. And it says, okay, where's your data? And I say, well, for sample 1, that's fraud. They've named it. They didn't call it variable 1, variable 2 this time. They actually called it fraud and firearms. So I pick the data. Notice it says, do you want to pool the variances? We check that this time because, yes, we want to pool them because we're assuming that the population standard deviations are equal. And we're doing a hypothesis test, so we leave it there. Let me move this over so you can see it a little bit better without the writing. Mu1 minus mu2, yeah, that's what we said. That's equal to 0. That's the null. That didn't look terribly like a equal, did it? Let's clean that up a little bit. Equal 0. And the alternative is that it's less than. So I need to change that. Right now it's a not equal. Oh, less than. And so I can just go do the computations, and it says, okay, my degrees of freedom 18. So notice there was 10 in each of these. They added them up 20 and then subtracted 2. T statistic. And I didn't pay attention to how far it wanted us to go. Usually it goes 2 decimal places. We'll go a few. Negative 2.75. Let's just say 0.961. We'll put the whole thing there. And the p-value, I don't know why I called that z. The p-value comes out as 0.0066. All right, and we'll use those to answer the question. So let's lower this back down. We can answer the questions. Now t rounded to 3 decimal places. Good thing I got enough decimal places going there. Let's get that out of the way. So negative 2.751. Oops, negative 2.751. So we got that right. Now let's go to the p-value. And I'll interpret the p-value after we put it in case it takes a while for it to register, to 4 decimal places, 0.0066. All right, remember what we do. We take that p-value and we say, oh, that's less than or equal to 0.1. See if it is. If it is less, then we reject the null hypothesis. Notice if I move the decimal 2 places, I get 0.66%. And that is, in fact, less than or equal to move the decimal 2 places 1%. So since it is less, I reject the null hypothesis. And I come to my conclusion that, yes, the data does provide sufficient evidence to say that the average time for for fraud, is less than firearms. So let's answer that. I'll write that down. So our answer, yes, the data provides sufficient evidence. And I'll shortcut this. that the mean time for fraud is less than the mean time for firearms. And if I had more room, I'd write that a little bit cleaner, a little more fully, but they're going to word it for us anyway, so I can go through. Now, I'm going to erase all that because we can remember that. Since the p-value is less than alpha, less than or equal to alpha, reject the null hypothesis, conclude that the data does provide sufficient evidence that the mean time served for fraud is less than that for firearms offenses. And so quickly as that, we use the p-value just like we did with one population means. We just have a slightly different test, but now we're able to test, do these two populations have the same or different values when we go to look at the population means of the two different values. Now, I probably shouldn't have just said next question because we're not going on to 9, we're actually going on to 10. So I'll have to pull up another problem, but that'll come up in just a second. But notice how similar this is to what we've been doing. Very much the same. A hypothesis test is a hypothesis test. So oftentimes what we do is just what we've been doing. We look at the p-value and compare it to whatever our significance level is. And if the p-value is less than or equal to alpha, we reject the null hypothesis. And then we go with whatever the alternative hypothesis told us. Okay, so here's problem 9. It's another hypothesis test, but what I want to do is I want to do 10, which is a confidence interval. So let's get this confidence interval going. And then what we can do is we will have seen both null alternative hypotheses, so a hypothesis test, and a confidence interval. And remember, the title of this chapter or this section was Inferences for two population means. So the inferences are both the hypothesis test and confidence intervals. Okay, so this is getting a little crazy waiting, but we will wait nonetheless. Should be up in just a minute, and we'll be able to do our confidence interval. And what you'll see, it's going to be very similar to what we did. We go into the same place. We just, instead of clicking on hypothesis test, we're going to click on confidence interval. All right. Again, and it's fraud and firearms again. Now, think about how this is going to work. Since we rejected the null hypothesis, the confidence interval, we would be guaranteed if that was a not equal instead of a less than or greater than, the confidence interval's not going to include 0 because we were saying there wasn't a chance they could be the same. So anyway, let's look at this. Preliminary data analyses indicate you can reasonably consider the assumptions for using pooled T procedures satisfied. Independent random samples of released prisoners in the fraud and firearms offense categories yielded the following information on time served in months. Obtain a 98% confidence interval for the difference between the mean time served by prisoners in the fraud and firearms offense categories. Now, I can enter the data again if I want to. This time instead, just to show you, I'm going to use the numbers they have down here because they've already calculated these. So instead of using the data, we're going to use the summary. So let's do that. And let me jot this down real quickly so we have it. So let's see, 1505, 3.15, 1923, and 4.66. All right, so I've got the means and I've got the standard deviation. So let's go to the confidence interval. We just go straight in and we open up. They're not letting us open it up straight from there. Let's go to question help. We'll open up StatCrunch from there. So apparently we couldn't have just put the data in anyway. We'd have to enter that by hand because I don't see anywhere where it's going to put the data in for us. So we open up StatCrunch and we go and we say, hey, stat, I want to do T stats to sample this time with summary. And it says, okay, what's the sample mean? Oh, I have those. I didn't get the sample sizes. Let's go check real quick. So the sample sizes, what do we have? 1, 2, 3, 4, 5. Oh yeah, we had 10 of each. We already talked about that when we did degrees of freedom. I knew that. Okay, so the sample mean, 15.05. The sample standard deviation was 3.15. Sample size was 10. The other sample mean, 19.23. So we see from looking at the data that there's a difference. The question is, could that just be sampling error, or is it because the population means are actually different? So I just put those in. Again, pool the variances. This time we're not doing a hypothesis test, we're doing a confidence interval. And had I paid attention to what the confidence interval was, I'd be in great shape, but I didn't. So let's go look real quickly. They said find a 98% confidence interval. All right. So make sure you put in the right number there. So instead of 95, that's a 98. And then just go compute, it's going to give you the interval. So let's see, let me jot this down. I'll just write it right underneath. We'll be able to see it that way. So my lower limit, negative 8.7199, and my upper limit, 0.3599. So with these values, since we didn't have a not equal, we had an inequality, 0 does happen to be in this interval. So we're going to look at how we interpret the negative versus the positive in these results. I think that's an important thing to understand. So that'll be good for us to understand since it's two different signs. All right, so to 3 decimal places. So from negative 8.719, that will round up to negative 8.72. And it's 720, but you don't need that 0. I'll put it in there so you think, hey, that's not 3 places. And then instead of 0.359, it's going to be 360. Again, and just to show you we don't need the 0, I'll leave it off on that one. Notice they didn't ask us to interpret, but I'm going to interpret anyway. Sorry about lost my voice there. So let me shut this down. I'm going to interpret this for you in case we have to interpret one of these. So it would go something along these lines. We can be 98% confident that the mean time, and we say whatever the first one is, the mean time for fraud, mean prison time if you want to, prison time. Oops, there's no I there. The mean prison time, I don't know why I put an I there. Let's erase that. Okay. So we can be 98% confident that the mean prison time for fraud is between. Now that negative means it's less. 8.72 months less to 0.36 months more, since it's positive, than the mean time. We'll even say the mean prison time. For firearms. All right, so that's the idea. A negative says the first population was less. A positive means the first population was more. And so we don't know exactly where it is, but somewhere. All right, so that's that section. What I'm going to do is I'm going to jump into the other section. There's not much difference. The only difference between that and what we just did, So what I'm going to do is I'm going to jump in. We're going to say, hey, let's do 10.3. I guess we can clear all of this off. Inferences for true population means sigma's not assumed equal. So we still don't know the population standard deviation sigma, but we think that they can't, we don't think they're the same value. So we can't make the assumption that they are equal. So same things before, when I go through and I do this, I still have the same assumptions. Simple random sample, independent samples, normal populations or large samples. Again, we usually use n greater than or equal to 30. And then lastly, this time, sigma sub 1 is not equal to sigma sub 2. And so we say if we cannot assume sigmas are equal, do not pool. That's it. Everything else is going to be the same. Still a t-test. We're still going to do it the same way. And so from there, I'm just going to jump in. We're going to do another problem. So let's see. Let's go back here. I already shut that down. I'm going to jump to problem 13. Hopefully that'll open up for us fairly quickly. And then what I'm going to do here, this problem is going to be both a hypothesis test and a confidence interval. So we'll be able to do both with the same problem. All right, so that should open up momentarily and we'll get going. All right, provided below are summary statistics for independent simple random samples from two populations. Use the non-pooled t-test and the non-pooled t-interval procedure to conduct the required hypothesis test and obtain the specified confidence interval. Okay, so they tell us, so this one a little bit different. They tell us it's a two-tailed test. Remember, a two-tailed test means if I'm looking at my normally distributed population, I may be way over here or I may be way over here. Either of those is too far away. So it's a two-tailed test. It means it's not equal to whatever this the assumed means were. And in this case, we're assuming they're equal. So the null hypothesis is that mu1's equal to mu2, or the other way to say that, remember, mu1 minus mu2 is equal to 0. There's no difference. The alternative hypothesis is that there is a difference. Mu1's not equal to mu2. Or similarly, the alternative is that mu1 minus mu2 is not equal to 0. So we just use the same thing. So we look, we say, okay, which one of these is it going to be? Mu1 equal, mu1 not equal to mu2. It's got to be C. We'll check that answer. That one's right. That was nice and quick. Find the T statistic. So again, we're going to find T, and we will also find the p-value. All right, so let's see. So again, non-pooled. So now when I go in, I need this data. So let me jot this data down. So I've got 14.2 and the sample size is 20. For the second one, I have 16.5 and 20. All right, let's take a look. So let's jump in. We'll open up StatCrunch again. I wonder if I can open up where I already have it. That would make life easier. There's StatCrunch. Well, let's do this. So we'll close that down. We'll clear all this stuff off. No, I don't want that. I don't want to clear that. And we go stat, t-stats, to sample with summary. All right, we'll move this over so you can see what I'm doing. Here. All right, so I jotted all this down. We had 14. Let's see. Standard deviation was 2, sample size was 20, 16, 5, and 20. And notice one had a sample standard deviation of 2 and the other had a sample standard deviation of 5. Those are getting pretty far apart. So just looking at those numbers, we would probably think, hey, you know what? These are pretty far apart. I probably shouldn't be able to assume that the population standard deviations are equal if the sample standard deviations are so far apart. But since I'm not making the assumption they're equal, I do not pool the variances. So leave it the way it is. So not pooled. We're doing a hypothesis test. Remember, this time we have mu1 minus mu2 is equal and mu1 minus mu2 is not equal. So it's already set up correctly for us. So we can go ahead and compute. Remind me to check if it's a 95% confidence interval when we get there. So I go to compute. That was quick. My t value, what did they do last time? 3 decimal places, negative 1.661. All right, I'm going an extra decimal place just in case. Negative 1.6609. And the p-value, 0.1093. 1093. All right, perfect. Now, so now we can go back. We'll just shut this down. Round to 3 decimal places, negative 1.661. And let's look at our p-value. So let me type that in, round to 4 decimal places, 0.1093. And remember what we do with that. We compare that, we say, hey, is that less than or equal to alpha's 0.10, which is my significance level alpha. Well, this time we have 10.93%. That is not less than 10%. So this time we do not reject the null hypothesis. That means we can't go with the alternative. So we have to say, no, the data is not sufficient to show that there's a difference in population means. So we would say something like, no, the data does not provide sufficient evidence. To say, and I'll just state it the way we wrote it here, that mu1 is equal to mu2. Helps? We don't state it in terms of the null hypothesis. The data is not sufficient to say that mu1's different than mu2. So it's not sufficient to say that. So we say, oh, they might still be equal. Our sample means were different, 14 and 16, but not different enough that we think the population means had to be different, at least not at the 10% significance level. So we say, excellent to that, makes us happy. What is the conclusion? Well, the conclusion was do not reject, there's insufficient evidence that the two means are different. So that's what we said. So that's D. And then from there, we're gonna go on to doing the confidence interval. Eventually, I'm gonna clear all this off. And then for the confidence interval, 90% confidence interval, 3 decimal places. So let's go back and pull up StatCrunch. It's already got our numbers in there, I think. Let's see. So if I go stat, T-stats, 2 sample with summary, now they're gone. We'll put them back in there. Let's see. 14 to 20, 16, 5, 20. Don't pool them. This time a confidence interval, and what they say, 90%. Oh, let's go ahead and compute. And we get a lower limit, and it said 3 decimal places. I'm all proud of myself for remembering. Negative 8.057 to negative 3.943. This is what I was talking about before. Notice those are all negatives. Well, if those are all negatives, what I'm thinking is population 1 had a mean somewhere between, I wonder if I put those in there. So sample difference was -6. Did I do a 16? And I can't see the data I put in. Well, let's check. Those numbers seem awfully big to me. I don't think they should be that big. I'm running it again because I'm not comfortable with that number at all. So let's try this again. Stat T Statistics, 2 samples with data. Nope, with summary. All right, let's try again. 14, 220. Oh, that's not a 14, that's a 10. What in the world am I doing? 14, 220, 16, 520. 16, 520. 90%. Oops. Now let's compute. Those numbers look a lot better than what I had before. All right, so those make me feel much more confident. So let's erase these. And let's see what we have. -4.057 to 0.057. Notice, so this is what I was trying to say. The other ones didn't match. 0 is in here. So there might not be a difference in the population means. And our conclusion was, hey, I can't reject the null hypothesis. There might not be a difference in the population means because they're different when I subtract them. If it's equal to 0, well, 0 is a possibility. I know 0's in my interval. So now we can go and enter that in. Now I feel better. And so let's go do that. Lost my problem. There it is. The 90% confidence interval is from -4.057. Oops. To 0.057. All right, so that's the end of it. Try these out. Hopefully the computer won't glitch as much as I did and take you so long to pull up the problems. But other than that, stick with this, work on it. Again, if we can assume the population standard deviations are equal, we pool the data. If we can't assume the population standard deviations are equal, we don't pool the data. That's the big thing in here. And of course, the fact that we're looking at 2 populations, comparing them as opposed to just 1 population. All right, well, with that, best of luck to you and stick with it because remember, you can do this.